So what we're going to do in this last video is get some practice interpreting absorption spectra using Tanabe Sugano diagrams. And you'll get a lot of practice on doing this in the homework. Basically, the entire homework, aside from one microstate problem, is about this. And so I just wanted to bring up this chart that we saw before without these examples. These were fully allowed transitions. Remember, these were like dyes, spin allowed, Laporte forbidden. These, right, spin allowed means you are going between like a quartet and quartet, doublet, didn't change the spin. Laporte means forbidden means you were going from G to G. So all D to D transitions, because all d orbitals are G, they're symmetric with respect to inversion, are Laporte forbidden. So D to D transitions are examples of these intermediate kind of extinction coefficients between 1 and 1,000. And then if you're spin forbidden and Laporte forbidden, those are going to be very weak transitions. These are, for example, D to D transitions for high spin D5. If you look at the Tanabe-Sugano diagram for D5 complexes, you'll notice that the ground state is actually a sextet, and there are no sextet excited states, and therefore you can't have any spin allowed transitions. So they're all spin forbidden, and because they're all D transitions, they're all Laporte forbidden. Examples of fully allowed ones would be ligand to metal charge transfers and metal to ligand charge transfers. So I'll explain what that is in a second, but I want to add to this list right here, because something people don't usually put together, is that tetrahedral complexes would fall into this. Spin allowed ones. Spin allowed D to D transitions. Okay, and why is that? That is because there isn't inversion for tetrahedral point group. So if there's no inversion, you can't be Laporte forbidden. So it's always Laporte allowed. The only question is, are you spin allowed or spin forbidden? So if you're spin allowed and you're in a tetrahedral if you're spin allowed and you're in a tetrahedral symmetry, you're going to be a fully allowed transition. All right, what about these ligand to metal and metal to ligand charge transfer? That is something like taking a metal from so this is our MO diagram, right, for an octahedral complex. That's like taking an electron and exciting it from the metal centered, right, d orbital centered electron, and going to one of these anti-bonding orbitals, going from metal to ligand. These are molecular orbitals that look T1U. So you went from G, T2G, G to U. So that is Laporte allowed. So it'll be a very strong transition, but it'll also be very high in energy. So there's a big energy gap. Similarly, there's ligand to metal charge transfers. So that would be something like a ligand down low, metal, electron on a ligand-centered orbital, right? T1U, for example, going to T2G. And that would be also Laporte allowed because you're going from U to G. There's a change in parity. So those will be very intense transitions. All right, so let's interpret this absorption spectrum. This is a cobalt hexa-aqua 2+ complex. Cobalt is in group 9. Oxidation state of cobalt here is 2+, so it's going to be D7. High spin or low spin? Well, you might not know, and so there's a couple ways to go about this. One is to analyze the Tanabe-Sugano diagram on both the high spin and the low spin cases and see which one matches the UV-vis spectrum. That's a way to actually figure out if you're high spin or low spin. That's an easy way to do so. But for the purposes of us just going through learning how to do this, let's look at the spectrochemical series. Water is over here. Generally, I can tell you as a rule of thumb for first row transition metals, cobalt's a first row transition metal, anything less than ammonia is a borderline case, but anything less than ammonia on the spectrochemical series is usually going to be high spin. Okay, it's pretty weak. Those are pretty weak field ligands. Now, when you get to second and third row transition metals, remember that those, for reasons we talked about in chapter 7, are usually low spin. So anyway, we're going to assume this is high spin because of that rule of thumb I just told you about ammonia and first row transition metals. So this is an octahedral complex. So we're going to use the D7 Tanabe-Sugano diagram. Now, if this were a tetrahedral complex, we'd have to use the D10-N diagram. So we'd have to use the D10-7 diagram. We'd have to use the D3 diagram. okay? But this is octahedral, so we're going to use the D7 Tanabe-Sugano diagram. So we pull that up from the handout that's given to us, and we're on the high spin side. So the high spin side is when we have weak field ligands. So the ground state here, it was derived from the quartet F free ion term, and the ground state is quartet T1, and it's going to be called quartet T1G. Why is it quartet T1G? We add the G because it's octahedral. Remember, this is a generic diagram. We have to add G's if we're going to be talking about octahedral complexes. And what we can see here is how many spin allowed transitions do we have? Well, we have the quartet T1G, so we can go to other quartets. Well, here's another quartet, other quartets to remain spin allowed. We can go to the quartet T2G. I showed it here. We can go to the quartet A2G. Okay, here you have to trace this line all the way up. And then there's also this quartet T1G right there. So there's going to be 1, 2, 3 peaks, okay? And so there they are. We can also know which ones are which. This is the lowest one, this is the intermediate one, this is the highest one in terms of energy. So that lowest one was this one. And so that's going to the quartet T2G. So it's quartet T1G to the quartet 2TG. There it is there. And I show the other ones here. So that gives rise to 3 peaks. There is some Jahn-Teller distortion, so you can see there's some splitting going on here. And then we have here, this is actually the beginning of a very large, high energy, right, high wave numbers transition. So this, if you went out into deep UV here, this would probably increase way off this spectrum here. And that is, a metal to ligand charge transfer, or that's a ligand to metal charge transfer, something that is Laporte allowed and thus has very high intensity. And so that's the basics of it. Now the homework, has to do with using the Tanabe-Sugano diagrams quantitatively. And I encourage you to use a ruler when you do this. The Tanabe-Sugano diagrams, unfortunately, are kind of small. And so you really have to pay attention to where you are. But basically, you're gonna, figure out where you are in terms of energy units by looking at, for example, the ratio between 2 peaks. So one hint for the homework is you can look at your first peak and like your second peak, for example, figure out the ratio of the energies between that, and then look at the Tanabe-Sugano diagram and ask yourself, okay, I know these are my 2 first lines for my 2 first transitions. Where do those ratios of energies equal what I'm seeing on my diagram? And so if the ratios are equal to what you're seeing, that can tell you where you are in terms of delta B. It can tell you how strong of a ligand you are. And then that can allow you to compute, for example, a third hypothetical transition or something like that, okay? So hopefully you'll be able to understand that. If not, please come get help from me. Also, these Tanabe-Sugano diagrams have the Rockoff values for common ions. So Cobalt 2, you can see here is 970 wave numbers. And so look for those as well. All right, guys, keep coming for help. If you need help, I'm happy to answer any questions that you may have. Thanks.